In this video, we want to prove the parallelogram identity. We will prove this identity in two different methods. The first method is based on a relation that we know between a complex number, absolute of a complex number, and its conjugate. Let me remind you this important identity for complex numbers. Absolute of a complex number, let's say the complex number is z, to the 2 is always can be written as z, the complex number, times by its conjugate. Our first method for proving this identity, which is famous to the parallelogram identity, is using this relation. Absolute of z to the 2 is z times z conjugate. Based on this identity, we can write absolute of z1 plus z2 to the 2 in the form of z1 plus z2 times by z1 plus z2 conjugate. And we can write z1, absolute of z1 minus z2 to the 2 in the form of z1 minus z2 times by its conjugate, z1 minus z2 conjugate. So we use this relation for this part and this part, and we wrote each of them in this form. Now let's simplify this. Now note that the conjugate of z1 plus z2 can be written as conjugate of z1 plus conjugate of z2. We have this relation for the conjugate of two complex numbers. Complex of z1 plus z2 is conjugate of z1 plus conjugate of z2. So we can separate conjugate. And if we do same thing for the other bracket, we can write this in the form of conjugate of z1 minus conjugate of z2. Now let's multiply the two brackets by each other. z1 times by conjugate of z1 is the first step. z1 times by conjugate of z1. Then we have z1 times by conjugate of z2. Then we have z2 times by conjugate of z1, which we can change the order and write it as z1 conjugate times z2. The order really doesn't matter in multiplication of numbers. And then we have plus z2 conjugate of z2. z2 conjugate of z2. Now let's multiply the two brackets that we have here. z1 times z1 conjugate, z1 conjugate. Then we have minus z1 z2 conjugate. Then minus z2 z1 conjugate, and finally we have plus z2 z2 conjugate. Now note that this term here with this term cancels, and this term with this term cancels. What remains here? We have z1 conjugate and same term here. These two terms are the same. So we have 2 z1 conjugate, and also we have 2 z2 conjugate. From these two terms, first note that we can factor it. Then we have z1 conjugate and z2 conjugate. Now let's use this important identity in complex number in the opposite order. If a complex number z multiplies by its conjugate, it can be written as absolute of that complex number to the 2. Z times z conjugate is absolute of z to the 2. So here we can write z1 times z1 conjugate as absolute of z1 to the 2. So we can write this 2 times absolute of z1 to the 2, and for this we have absolute of z2 to the 2. And this is the other side of the identity that we wanted to prove. So we prove that with starting from this and writing it in this form, we prove that this equals to that. This is the first method, and this method is based on this important identity that we know in complex numbers. The second method is more algebraic method. So we want to prove that absolute of z1 plus z2 to the 2 plus absolute of z1 minus z2 to the 2 is always equal to 2 times absolute of z1 to the 2 plus absolute of z2 to the 2. In this method, we suppose z1 to be a plus bi, because z is a complex number, so we can suppose z1 is a plus bi. And we suppose z2 as c plus di. These are two complex numbers, so we suppose each of them equal to a plus bi and c plus di. We know that any complex number can be represented in this form. Now we substitute these in two sides of this equation, and we will show that these two sides are equal to each other. If we substitute this in the left, we have absolute of z1 plus z2. What is z1 plus z2? It equals to a plus c plus b plus d times I. Attention, when we add z1 to z2, we have to add real parts to each other and imaginary parts to each other. A and c are real parts, so we wrote them here. And bi and di, we add them together and we have this term here. What about z1 minus z2? It equals to a minus c plus b minus d times I. What about right side? In the right side, we have 2 times, what is absolute of z1? Absolute of a plus bi to the 2 plus absolute of c plus di to the 2. So we have to show that this to the 2 plus this to the 2, I forgot to put the powers here, is equal to the other side. Now remember, what is absolute of a complex number? Absolute of a complex number, let me remind you, if we have z equals x plus iy, then its absolute is a square root of real part to the 2 plus imaginary part, which is y to the 2. So in the left side, absolute of a plus c plus b plus di to the 2 is basically a square root of a plus c to the 2 plus b plus d to the 2. This is the real part to the 2, imaginary part to the 2. And don't forget we have a power 2 outside, so this radical raises to the power of 2. And we know that the power 2 and radical cancel each other. So left side of this is basically a plus c to the 2 plus b plus d to the 2. The next absolute is a minus c to the 2 plus b minus d to the 2. What about right side? In the right side we have 2 times. What is absolute of a plus bi to the 2? The absolute of a plus bi is radical a2 plus b2. But when we raise this to the power of 2, the power of 2 and radical cancels. So it equals to only a2 plus b2. And the absolute of c plus di is c2 plus d2. If we simplify the left side, simply we can see that it equals to the other side. In the left side we have a plus c to the 2. If you multiply a plus c by itself, or if you use the identity, simply you can see that it equals to a to the 2 plus ac plus ca, it is 2ac, and c times c is c to the 2. So a plus c to the 2 is a2 2ac c2. So this equals to a2 2ac c2. The next bracket is b2 plus 2bd d2. The next bracket is a2 minus 2ac, because in the middle we have minus 2ac plus c2. And the next bracket is b2 minus 2bd and plus d2. Now, attention. Let me fix this b here. It is b to the 2. Now, if you attention, 2ac with negative 2ac, 2bd with negative 2bd cancel. What remains? a2 and a2, 2a2. And we have 2b2 and 2c2 and 2d2. Of course, we have a power 2 here. So, this expression is exactly 2 times a2 plus b2 plus c2 plus d2. And it is equal to the other side. And this is the second method to prove the parallelogram identity. But why they have named this parallelogram identity? If we draw a parallelogram here, and if we suppose this side of the parallelogram as Z1 and this side of the parallelogram as Z2, then this diagonal of this parallelogram is basically Z1 plus Z2, and this diagonal of the parallelogram is Z1 minus Z2. So these two sides are Z1 and Z2. The two diagonals are Z1 plus Z2 and Z1 minus Z2. Let's name this vertex A, here B, C, and D. In geometry, we have this simple important fact that the sum of squares of the diagonal of a parallelogram, so AC to the 2 plus BD to the 2, these are the diagonals of this parallelogram, is always equal to AB to the 2 plus the other side BC to the 2 plus CD to the 2 plus DA or AD to the 2. We have this fact in geometry. But we know that in a parallelogram, BC, this side, the length of this side and the length of this side are equal. So we can replace BC to the 2 here with AD to the 2. So let me replace this with AD to the 2. And CD and AB are equal. So CD to the 2 is also AB to the 2. So we have this fact in geometry. Now look at this. We have 2AB to the 2 and 2AD to the 2. And in the left we have AC to the 2 plus BD to the 2. Look at this. This is exactly the parallelogram identity in complex numbers. AC is basically Z1 plus Z2, but not Z1 plus Z2, absolute of Z1 plus Z2. Because AC is the length of diagonal AC. So this is absolute of Z1 plus Z2 to the 2. BD to the 2 is the other diagonal, the length of the other diagonal to the 2. And in the other side, we have 2 times AB, which is Z2 to the 2, absolute of Z2 to the 2, plus AD, which is absolute of Z1 to the 2. As you can see, the identity that we proved in complex numbers is basically the simple fact in geometry. And it is related to a parallelogram. I hope you liked this video. If you liked this video, please subscribe to my channel and see you in the next videos.